Hello everybody, welcome into another lesson. So today we are going to talk about applications of determinants. So far with determinants, we've of course evaluated them. We've also been able to apply them to determine if a matrix is invertible or not. Of course, if a determinant equals 0, it's not invertible. We've also, just in the last lesson, used Cramer's rule, which involved the use of determinants to solve a system of equations. But there are many other uses. We'll cover a couple of them today. The first use, you can actually use determinants to solve for the area of a triangle that's given by three different coordinates in the coordinate plane. So here you have points P, Q, and R with their various x and y coordinates. The area of a triangle is equal to plus or minus 1/2 the determinant of x1, y1, 1, x2, y2, 1, x3, y3, 1. And that plus or minus 1/2, so it's going to depend upon what value you get for the determinant. If you get a positive value for your determinant, you'll take the positive of 1/2. If you get a negative value for your determinant, you need to take negative 1/2 because the area should always be positive. You can't have a negative area, so that's where that plus or minus 1/2 comes in. So let's go ahead and do a couple of examples for finding a triangle. So let's say I have point P given at the point -2, 4. Point Q given at the point 2, 3, and then I have point R given at the point -1, 5. So let me just draw a rough draft of this triangle here. So there's about -2, 4. So here's P. Q is about 2, 3, right about there. R is -1, 5. We'll put R right there. So let's connect the dots here. Here is our triangle PQR, given these 3 points. We want to find the area of this triangle. Well, to find the area, we're going to take plus or minus 1/2, again, depending upon whether our determinant's positive or negative, because the area always needs to be positive. The determinant is your x1, y1 coordinate, and then a default 1 for your third entry in the first row. Then take your q coordinate, so your x, y, and then just a default 1 for your third entry in the row, and then your third point, so your x and your y value, then a default 1 for your last entry in the row. So the area of this triangle is equal to plus or minus 1/2 times the determinant of -2, 4, 1, 2, 3, 1, -5, 1, 1. Well, I think it's best we use the third column. Let's go down the third column here, alright? So let's just take the determinant here. Let's ignore that plus or minus 1/2 for just a minute. That might be in our best interest. Alright, so we're going down the third column. So the first entry in the third column is a 1, so I need to take positive of that 1 times the resulting determinant of when I strike out the column and row in which that 1 occurs. So that'll be the determinant of 2, 3, -1, 5. Alright, so there's that. And then we're going to use the second number in the third column. So we'll take that one. According to the coefficient determinant, that should be a minus the resulting determinant. So When we strike out the row and the column in which that one occurs, the resulting determinant will be a 2 by 2 with -2, 4, -1, and 5. Then we have one more 2 by 2 determinant to evaluate. Alright, we're going to use the final one in the third column. So according to the coefficient determinant, that should be plus that one. So plus the resulting 3 by 3 determinant of what's left when we strike out that row and that column in which that one occurs. The resulting 2 by 2 determinant is going to be -2, 4, 2, and 3. So now we'll just solve these three 2 by 2 determinants, which would end up giving us, let's see, 2 times 5 is 10, minus 3 times -1, that'd actually be plus 3, minus this determinant here, -2 times 5 is -10, minus 4 times -1, that actually turns into plus 4, plus the last determinant, you would get -2 times 3 is -6, minus 4 times 2, that's -8. So let's simplify here. You would get 7 minus, all right, so you have -10 plus 4 is -6, -6, that's plus 6. Then -6 minus 8, that's minus 14. So you have 7 plus 6 minus 14, which is 13 minus 14, gives you -1 for your determinant. So the area, since our determinant is negative, that means we need to take -1/2 times that -1 so we can get a positive area. That means the area of this particular triangle is equal to 1/2 square units. So we get an area of 1/2 square units for triangle P, Q, and R. Alright, let's do one more general triangle here. And then we'll do a couple where we got to solve for x. I didn't bring out the graph magnet today because I wasn't going to get that deep into graphing, so alright, so the next one, point P has the point -3, 5. Point Q has the point 2, 6, and then we have point R has the coordinates 3, -5. Alright, so we're trying to find the area of a triangle with points P at -3, 5, Q at 2, 6, and R 3, -5. So let me draw a rough sketch of that here. Q is at 2, 6. R is at 3, -5. So let's go ahead and connect the dots here, and you'll get a rough representation about what this triangle is going to look like in the coordinate plane. So there's triangle PQR. We need to find the area of that particular triangle. So again, the area equals plus or minus 1/2, and we'll know which one we need to use when we get the value of the determinant. Plus or minus 1/2 times your first row in the determinant would be that -3 and 5 for your first coordinate, and then always put a 1 for your third entry in the row, and then your Q coordinate of 2, 6, and then add a default 1, and then your R coordinate of 3, -5, and add a default 1. So the area equals plus or minus 1/2 times the determinant of -3, 5, 1, 2, 6, 1, 3, -5, and 1. Again, I think we'll go down the third column. That might be the easiest since all the coefficients are 1. So let's just focus on this determinant a minute. Forget that plus or minus 1/2. So negative 3, 5, and 1, 2, 6, and 1, 3, negative 5, and 1. Alright, so we're going to start in the third column. The first entry is a 1. According to the normal coefficient determinant, that needs to be positive. So positive of the resulting determinant when I strike out the column and row in which that occurs, your resulting 2 by 2 determinant is going to be 2, 6, 3, and negative 5. So there's your first 2 by 2 determinant. And then we're going to do the second, we're saying the third column, do the second entry in the third column. According to the coefficient determinant, that should be a negative on that 1. So that'll be the minus of the resulting determinant when we strike out the row and column in which that one occurs. You'll end up with the determinant of negative 3, 5, and then 3, negative 5. And then we're still going to have one more 2 by 2 determinant to contend with. Alright, so we're going to pick the third entry in the third column, which is a 1. According to the coefficient determinant, that 1 should be positive. So plus the resulting determinant of what's left when you strike out the row and column in which that one occurs, you'll end up with, if I can quit dropping stuff, the determinant of negative 3, 5, 2, and 6. Alright, so there's our 3 determinants. Let's go ahead and do them. So 2 times negative 5 is negative 10, minus 6 times 3, so that's minus 18. Minus your next determinant. Alright, negative 3 times negative 5 is positive 15. Minus 5 times 3, that's negative 15. Plus your final determinant. Well, negative 3 times 6 is going to be negative 18. Minus 5 times 2, which is 10. So when we simplify this, okay, negative 10 minus 18 is negative 28. 15 minus 15 is 0, so minus 0. And then negative 18 minus 10, that's another negative 28. So we get negative 56 for the determinant. Now that means that area is going to equal what? Well, since our determinant's negative, we need to take the negative 1/2 to make the area positive. So we'll take negative 1/2 times negative 56, which would give us an area of positive 28 square units. So the area of triangle PQR would be 28 square units. Alright, now I'm going to leave the coordinate plane up a minute here, but these next couple I'm not going to draw, because believe it or not, we're about to have a missing coordinate we got to solve for. I'll even leave the frame up. How about that? I'll even leave the frame up here for the determinant, but let me leave the framework for the points up too. Alright, so where am I going with this? Well, we are given such that we have point P has the points negative 1, 5. Point Q has the point negative 2, 0. And then point R has the point x2. We don't know the x-coordinate of point R. That's what we need to seek to find. They tell us in this case that the area of the triangle is 4 square units. So we do have an area of 4 square units, so we know the area. Well, that means right off the rip, we got a positive area, so we need to have a positive value on the determinant. So that'll be 1/2 of that determinant, which would be point P, you'll put in -1, 5, and 1. And then Q, you would put in -2, 0, 1. R, you would put in x, 2, and 1. All right, so there's your determinant. Well, right away, what do we notice? If 1/2 of this determinant equals 4, that means the value of this determinant itself, if you multiply both sides by 2, should actually equal 8. So we have a framework now for that this should equal 8 when we multiply both sides by 2. So now let's take this determinant here and get the x value that would give us an area of 8 square units. So I'm going to go down the third column again. So we'll take +1 times the resulting determinant of what's left when you strike out the row in the column that one's in. You would end up getting the determinant of -2, 0, x, and 2. All right, so now you're going to end up having, let's see, whoops, I probably need to set up my next determinant, right? We're going to take the second number in the third column, so that should be minus that 1 times the resulting determinant I get when I strike out that row and column in which that one occurs. So that resulting determinant is going to end up being -1, 5, x, and 2. And then that means I should actually end up having one more determinant. So this would be what? -2, 0, all right, 1, 1, 1. Sticking with the third column, the last entry, we should take positive of that 1 times the resulting determinant of whatever's left when I strike out that row and that column in which that 1 lies. The resulting determinant would end up being -1, 5, -2, and 0. Let's simplify this a bit here. So in the first determinant, -2 times 2 is -4. Minus 0 times x, that's just -0. Minus your next determinant, well, -1 times 2 is -2. Minus 5 times x, so that would be -5x. Plus your final determinant, all right, so -1 times 0 is 0, minus 5 times -2 is actually +10. All that should equal 8. So we should end up getting -4 plus 2 plus 5x plus 10 equals 8, which means that 5x, so -4 plus 2 is -2 plus 10. -2 plus 10 is going to end up being 8. So 5x plus 8 would equal 8. So that means then that 5x equals 0, which means I should get an x value of 0. So the x-coordinate of point R that would give us an area of 4 square units is going to be 0. So R will have the coordinate 0, 2. And I'll do one more problem like this. Let's see what we're up against this time. The area should still be 4 units. That much is true. That hasn't changed, but what we seek to find is about to change. So all right, let's see. So we have -4, 2, -3, 5, and then -1, y. This time we don't know the y coordinate of r, but that's okay. We can easily find that because the area of the resulting determinant times 1/2 would equal 4. So since we got the positive area, we definitely want to keep a positive 1/2 on the determinant. So the determinant would end up being your coordinates for point P, -4, 2, and then a 1. Point Q, -3, 5, and 1. Point R is -1, y, and then a 1. So there's your determinant. Well, if we multiply both sides by 2, that means your area should actually then, your area would equal 8. Well, not 8, but you multiply both sides by 2, you get that the determinant here, that -4, 2, 1, -3, 5, 1, -1, y, 1, that whole determinant should have an area, or not an area, but a value of 8. Now we just go through, set up our 3 2x2 determinants. Let's use the third column again. So I'm going to do that first one, so that'll be positive of the resulting determinant when I strike out the row and column in which that one lies. So the resulting determinant is a 2x2 with entries -3, 5, -1, y. Alright, so there's your first 2x2. Now your second determinant, we're going to go down the second entry in the third column, so that'll be minus the resulting determinant of what's left when you strike out the row and column in which that one lies. So let's do that. You'll end up with the resulting determinant of -4, 2, -1, and y. Then we should get one more determinant. All right, let me fill this back in first so we get accurate determinants. We're going to use the last entry in column 1, so we need to, it's going to be positive of the resulting determinant of what's left when we strike out the row and column in which that one occurs. So you should have the determinant of -4, 2, -3, 5. All these determinants equal to 8. Now let's go ahead and simplify the left-hand side. So in the first one, you'll get -3 times y. Well, that's -3y. -5 times 1, -5 times -1, that's actually +5. Minus your next determinant, well, -4 times y is -4y. -2 times -1, that's +2, plus your final determinant. All right, -4 times 5 is -20, -2 times -3, that's +6. All that should equal 8. So you should end up getting simplified into -3y plus 5 minus -4y, that's +4y, -2 minus 14, all that equals 8. do your like terms. 4y minus 3y is simply y. All right, 5 minus 2 is 3, minus 14 is negative 11, so y minus 11 equals 8. That means y should have a coordinate of 19. So the y coordinate that fits for this should be 19 for point R. So that's how you would find missing coordinates when you're given an area of a triangle when you're using determinants. Alright, now I have a couple other problems that are similar, but we're not going to be doing triangles per se. Not at all. In fact, we're going to be given a couple quadrilaterals. We're going to do 2 quadrilaterals. So let's see here. Point P has the point negative 3, 2. Point Q has the coordinates 1, 2. R has the coordinates negative 5, negative 4. And then S has the coordinates negative 1, negative 4. Alright, so I have 4 vertices this time. Let's go ahead and connect these dots. So negative 3, 2, right about there. So there's P. Q is about at 1, 2. Here's Q. R is about at negative 5, negative 4. And then S is at negative 1, negative 4. That'd be right about there. So here's your S. Let's go ahead and connect these dots here. Alright, so you notice here we actually have a quadrilateral by points Q, R, and S. Well, we don't really have a formula for the area of a quadrilateral using determinants, but we can derive one. Isn't it true for any quadrilateral, virtually any quadrilateral, you can split these into 2 triangles? If I draw a diagonal from P to S, I now have 2 triangles. So I can solve for 2 different triangle areas and get the total area of the triangle, of the quadrilateral. So the area of quadrilateral PQRS equals the area of triangle. We split this into triangle PRS plus triangle PQS. Remember all the way back to geometry when we had the area addition postulate. If you have a figure split into 2 or more figures, the total area is just the sum of the areas. So that's how we can find the whole area of the quadrilateral. Now, let's seek to find the area of PQRS. Or I think we know we're going to find the area. Let's just look at triangle PQRS or PRS. The area, that's going to equal plus or minus 1/2 times the determinant of your points P, negative 3, 2, and then a default 1, and then R is negative 5, negative 4, and then a default 1. S is a negative 1, negative 4, and a default 1. Alright, so there's your triangle. There's for the area of triangle PRS. Let's go ahead and evaluate the determinant. So we got negative 3, 2, 1, negative 5, negative 4, 1, negative 1, negative 4, 1. Let's go ahead and find these determinants. So let's go down the third column. I take positive of that 1 times the resulting determinant. So let's strike out the row and column in which it occurs. You get the determinant of -5, -4, -1, -4. All right, let's see. We had P, which was -3, 2, 1, 1, 1. All right, the next entry in the third column is that one. We need to take minus that 1 times the resulting determinant of what's left when we strike out the row and column in which that one occurs. We end up with a determinant of -3, 2, -1, -4. Then we should have one more determinant. PR, all right, so -5, -4, 1, 1, 1. And then we got one more, take positive of that 1. Again, a scam call, don't mind them. So take positive of that 1. That's going to be plus the resulting determinant of what's left when we strike out that row in that column. We end up with -3, 2, -5, -4. All right, so let's go ahead and simplify all this. So the first determinant, -5 times -4, that's positive 20, minus -4, so positive 4 times -1, that's -4, minus your next determinant of -3 times -4, positive 12, minus 2 times -1, that's actually plus 2, plus the next determinant of -3 times -4, that's positive 12, minus 2 times -5, that's plus 10. So let's go ahead and simplify. 20 minus 4 is 16. 12 plus 2 is 14, so 16 minus 14. And then plus 12 plus 10, that's plus 22. Well, 16 minus 4 equals 2, plus 22 is 24. Now to find this area, we just take, since the determinant was positive, that means we need to take positive 1/2. So that would just be 1/2 times 24. That means I get an area of 12 for triangle PRS. So I think we'll go ahead and I'll put the area up here. Area of triangle PRS equals 12. All right, now we're only halfway done because we also have to evaluate for triangle PQS to find the second triangle. So we're going to do PQS this time, that area. So in your determinant, still put in point P, so -3, 2, 1. Point Q was 1, 2, and 1. Point S was -1, -4, 1. So the area will equal plus or minus 1/2 of this determinant. So just focus on the determinant a minute. So we'll have -3, 2, 1. 1, 2, 1, -1, -4, 1. All right, so let's go down the third column again. Well, that's going to equal this positive 1 times the resulting determinant of what I get when I strike out the row and column that 1 occurs in. I get 1, 2, -1, -4. So let's go ahead and I might have to repair this a couple times. Now the second entry in the third column, that's going to be minus that 1 times the resulting determinant. When we strike out the row and column where it occurs, you end up getting -3, 2, -1, -4. And we should have one more determinant to worry about. Alright, so the final one, that should be +1 times the resulting determinant of what's left. When I strike out the row and the column in which that one occurs, you end up with -3, 2, 1, 2. Alright, so there's your three resulting determinants. Let's simplify this. So 1 times -4 is -4, minus 2 times -1, that's +2, minus your next determinant. So -3 times -4 is actually +12, minus 2 times -1, so +2, plus the last determinant. So -3 times 2 is -6, minus 2 times 1, that's another -2. So simplifying this, we end up getting -2. 12 plus 2 is 14, so -2 minus 14. And then 6 minus 2 is -8. So -2 minus 14 is -16, minus 8 is going to be -24. Since the determinant is negative, I need to take -1/2 this time. So the area would equal -1/2 of -24, which would end up giving me +12. So now we have the area of triangle PQS also equals 12 square units. So we found the area of both triangles. Now it's just easy. This is real easy because we now know the area of both triangles. So the area of quadrilateral PQRS equals the area of triangle PRS, which is 12, plus the area of triangle PQS, which is also 12, giving you an area for this quadrilateral of 24 square units. So whenever you have other objects besides triangles, generally you can split them into other triangles and just take the determinant of separate triangles and find the area that way. Alright, so there is one more topic to cover for applications of determinants. That's testing for collinear points. I think we can erase the graph now. So there's that term from geometry all the way back then, collinear points. That just means points on the same line. So we're going to test for collinear points. So let's say again I have points P, some x1, y1, a point Q, where I have some x2, y2, and then I have some point R that's going to be x3, y3. I want to determine, are these 3 points collinear? Do they lie on the same line? The answer for that's actually quite easy. It's pretty similar to finding the area of a triangle. You'll set up in your first row your x1, y1 coordinate, then a default 1. Row 2 is your x2, y2 coordinate, then a default 1. And then row 3 is your x3, y3, then a default 1. If it equals 0, then P, Q, R are collinear. If the determinant does not equal 0, then P, Q, R are non-collinear. So in order for these 3 points to be collinear, the determinant of these 3 points with that added 1 in the third column of each row, that determinant must equal 0 in order for them to be collinear. If you get any other number but 0, they are not collinear. It's really that simple. So let's go ahead, we'll keep the format here. We'll do a few of these. So let's see what we get. Point P, let's see. Point P, we have 3, -1. Point Q, we have 0, -3. Point R, we have 12, 15. Or is it 12, 15, 12, 5? Ugh. It's 12, 5. Okay. So we have points P, 3, -1, Q, 0, -3, R, 12, 5. We want to determine, are these 3 points collinear? So let's take the determinant. Top row is all point P, so 3, -1, a default 1 in the third entry. Second row, point Q, 0, -3, then a default 1. Point R is your third row, 12, 5, and a default 1. Like before, I'll just go down the third column. So that's going to be +1 times the resulting determinant of what's left. When I strike out that row and column where it occurs, I'll end up with 0, -3, 12, and 5. Now we got 2 more determinants to evaluate. Use that second one, that should be minus the resulting determinant of what's left when I strike out that row and that column. So I'll end up with 3, -1, 12, 5. And then I'll have to do one more determinant. Alright, so we got 0, -3, and then 1, 1, 1. Use that last one in the third column. That'd be plus the resulting determinant when we strike out the row and column that one's in. You'll end up with 3, -1, 0, -3. Alright, so let's simplify. First determinant is 0 times 5, which is just 0, minus -3 times 12, that'd actually be plus 36, minus your next determinant, 3 times 5 is 15, minus -1 times 12, that'd be plus 12. And then you end up having your final determinant, 3 times -3 is minus 9, minus -1 times 0, that's plus 0. So if we simplify this, you'll end up getting 36 minus that 15 plus 27. So that'd be minus 27 minus 9. You get 9 minus 9, which equals 0. So yes, these points are collinear, in fact. They are collinear because your determinant is equal to 0. Alright, so getting a 0 determinant makes these points collinear, otherwise they're not collinear. Okay, let's do another one. We'll have some different P, Qs, and Rs. We got 3, -5 for point P, 6, 1 for Q, 4, 2 for R. The big question is, are these 3 points collinear? Well, let's set up our determinant. First row is point P, so 3, negative 5, 1. Second row, point Q, so 6, 1, 1. Third row, point R, 4, 2, 1. Let's go down the third column again. So the first one will be positive 1 of the resulting determinant when we strike out that row and column in which it occurs. That would be the determinant of 6, 1, 4, 2. All right, let's set up two more determinants here. The next one in the second column, that'll be minus the resulting determinant of what's left. When we strike out that row and column. So the resulting determinant is 3, negative 5, 4, 2. And we should have one more determinant. And the final entry in the third column, that should be plus the resulting determinant of what's left when we strike out that row and column. So let's see here. Let's do, the determinant would end up being 3, negative 5, 6, and 1. Let's simplify. So the first determinant is going to give you 6 times 2, which is 12, minus 1 times 4, which is 4, minus your next determinant. So 3 times 2 is 6, minus negative 5 times 4, that's actually plus 20. And then plus your final determinant of 3 times 1 is simply 3, minus negative 5 times 6, that's plus 30. Let's see what we get when we simplify. 12 minus 4 is 8. Inside the brackets, 6 plus 20 is 26, so 8 minus 26. And then 3 plus 30 is going to be plus 33. So 8 minus 26 is negative 18. Plus 33 is going to end up being 15. Well, you got something other than 0. The value of the determinant was 15, so these are non-collinear points. So these 3 points, in this case, because you got a determinant value other than 0, means they are non-collinear. So that's how that works for finding collinear points. So some of you are probably going to be excited about this, but this was the last lesson for the matrices and determinants unit. Now, that doesn't mean we won't see them a little bit again in the rest of the course. They do have other uses, but that'll come further down the line when we get into more advanced trig in this course and polar coordinates and all that, and vector cross products and so on. But the next lesson we are starting the sequence and series unit. We'll talk about sequences in general. So I hope everyone has a great day. Take care.